So now with derivatives, we went from displacement to velocity to acceleration. And with integrals, we can go backwards from acceleration to velocity to displacement. So you can see that in an exam question, they like to start with velocity because it's right in the middle. Then they can check if you can do the derivative by going to acceleration. They can check if you can do the integral by going back to displacement. The acceleration of a particle moving in a straight line at time t is given by a equals t plus 1. And we've got some initial conditions here. So we can work backwards from acceleration to get to velocity. And when we do that, we're going to have a plus c. And you can probably see here that you might want to put a C1 here, or you might want to use C and then D, because we're going to work backwards again and have another plus C. You can plug in the initial condition that you know that when time is 0, the velocity is 8. So we get our velocity formula. And then from there, we can do the integral of our velocity formula to get our displacement formula. So I used a different letter. I was worried I'd use C again. I used K this time. And then we can solve for K by putting in our initial condition. And plug it in to get your final equation. I find for the most part, kinematics questions are straightforward. Yeah, we got a couple of challenging ones today, and for those of you that have taken lots of physics, you're going to have to refrain from trying to use all your physics formulas. The velocity of a moving object is given by 50 minus 10t. Find the acceleration. So now we're doing the derivative. Negative 10 meters per second squared. Okay. One thing to be careful on in these questions is units. I think you guys have been starting to get used to being trained to make sure you're checking for units and including it all the way through. But that's just something to remember. If the initial displacement is 40, so that means when time is 0, s is 40, find an expression so we can integrate our velocity. You wouldn't have to write this step. You could probably directly go to here and that would be fine. Plug in 0, solve for c, and you can write your equation. So try number 3 on your own. And I'll put up the answers in a second. I'll put up the answers for A and B so you can check if you're doing all right. And then you can try C and D on the next page. And here are the answers to C and D. When a particle is at rest, that means its velocity is 0. So you'd go to your velocity equation, plug in 0. Then we found t equals, this is a unit here, 3 seconds, and t equals 1 second. And then for D, once you have those, you can plug them in. So now we're going to look at the difference between displacement and distance. And I think for me, this is a main reason why I find it so hard to exercise by running. Because if I want to go for a jog, I go out my front door, I run around for a while, and where do I end up? Right at my front door again. And mathematically, I say I could have got here a lot quicker just by staying here. And I wouldn't have had to go through all that pain of running, because by going around the block, I know it's good for my health and everything, but my displacement is 0. Like, if all of my cars didn't work and all my bikes had flat tires and I had to get somewhere a kilometer away in a hurry, then I feel like I could run and do that. I would have purpose. But just running around the block and ending in the same place, I don't know, doesn't do anything for me. So I would have gone a distance. I would have ran a kilometer. That would have been the distance I ran. But my displacement is 0 because I get right back to where I started with. Now we're going to see with integration that if we have our graph of velocity, the area under the curve is your accumulation of change. So the area under the curve accounts for your displacement. And when the area is under the curve but below the x-axis, that displacement is negative. This displacement is positive. So this is saying from A to the origin, you've gone away from your house. You've created some sort of positive displacement. From the origin to this next intersect, in A2, you've headed back a certain amount. This amount looks like it's a little bit less. You forgot something, and you almost got there, and then you realized, oh, I have it, so now I can travel where I want to go. And in A3, you have a positive displacement again. So displacement has positives and negatives. Anything that's below the x-axis, that area is considered negative. And if you added up all those, you would get your displacement. So displacement is just the integral of your velocity. If we want to find our distance, we need to make this section positive. So what we could do is we could break everything up and then make sure we take this part and put absolute values around it. Or you could and on the graphing calculator, this is really handy. Can you see that if you flip the original function, if you took the original velocity function and made it absolute value, that would flip that part of the graph up? And then all of your areas under the curves would be positive? I like that if it's a calculator question, because you can really easily just go, okay, I don't have to figure out where it switched from positive to negative. I can just do the absolute value of the whole function and then add up the 3 areas. But if it's non-calculator, I'd probably have to figure out where these different parts are, because the integral of the absolute value is not easy to do without a calculator. In fact, we don't have a chain rule idea yet for doing that. So we're on the edge of a cliff, and we have a golf ball in our hand, and it's not a very good golf ball that you want to keep it. You're like, this looks like it would be fun to throw. Have you ever been in situations where you're at something, you've got a rock, and you're like, this would be fun to throw at this moment? Edges of lakes. I can think of a lot of good places not to throw rocks in my math class. Uh-oh. Okay. So a golf ball is thrown upward with a velocity of 7 meters per second from the edge of a cliff 75 meters high. How long will it take the golf ball to hit the ground at the bottom of the cliff? And this sounds very much like a physics question, because it is as well. But the idea here is, can we take what we know and just use calculus without any physics formulas to figure this out? And the answer is yes. We know this one fact, so you have to know gravity. So we've got our acceleration. And if we have our acceleration and we know an initial velocity and an initial displacement, we can integrate backwards to find these equations. So my velocity will be this integral with a plus c. And I know I'm going to do two c's here, so I have a plus c1. I plug in my initial condition, which should have a 7 here. And we have our equation for our velocity. Yay, there's a picture. Oh yeah, there's definitely water there, because that would make it more fun to throw. Then to find our displacement, we integrate again. Here I have a plus c2 because I already used plus c1. And these initial conditions where the time is 0 is really nice, because the math is super easy when everything can sort of go away. So we've got our displacement formula. And then the question is, when does it hit the ground? Well, that's when it's going to be at 0. Solve this with a graphing calculator or the quadratic formula. If it was non-calculator, you could leave it as a quadratic formula. You get 2 answers. But since this is a real-life question, one of the answers is negative 3.26. Okay? That would mean I'm on the cliff, I throw the rock, and 3 seconds before I threw it, it hit the water. That's what that means. So obviously we have to cancel that out. That's not a very reasonable answer. This one, I would say, is a pretty straightforward one where you can start with acceleration and use calculus to find all the other formulas. For those of you that have taken physics, you can now analyze this with your formulas you've used in your physics classes and see how they're related and how they're connected. Okay, a little bit harder one. Nathan designed a car that would increase its speed steadily until it reached 100 kilometers. You just hit a button and just, fancy new cars these days, all the electronics. This wouldn't be hard to do. One day he set out on the highway and reached his cruising speed of 100 kilometers per hour 20 seconds later. How far did he go in those 20 seconds? Again, the crazy thing about these questions is you feel like when they ask the question, you're like, whoa, wait a minute, you haven't given me nearly enough information. This seems very complicated. And this one is a little bit more complicated than the last one. But we can use our calculus to figure this out. Okay? First of all, we'll probably have to do some conversions here, because we've got 100 kilometers per hour, we've got seconds, we've got meters. So we're going to want to deal everything in the same units. So 100 kilometers per hour times 1,000 would be 100,000 meters per hour. In an hour, there is 3,600 seconds. So we can translate 100 kilometers per hour by dividing by 3,600 to convert it to seconds to get 27.7 meters per second. So some conversions to begin with, just to have our units. Or we could do everything, we can do everything in kilometers per hour and change that. When you change your units, really doesn't matter as long as you make sure that you change them. I'm going to leave that 27.7 as the fraction that I came up on my calculator. It ended up being 250 over 9 meters per second. We know that our final velocity was 100. Our initial velocity starting at 0, which is really easy to convert. 0 kilometers per hour. Quickly do all the calculations, is exactly equal to 0 meters per second. Whew. What do we know? We know something at time 0. We know something at time 20, and I got creative here. I used a new Greek letter. You can use, feel free to use K if you don't. This is the Greek letter lambda. Just having fun. But you can use any variable you want here, like K or X. So your acceleration is some constant, but we don't know what it is. But we know that the integral of acceleration is our velocity. So if this is if you want to use K instead, this upside down Y is kind of weird. But you're just going to have whatever, if it's a 3, 3t, if it was a 10, 10t, if it's k, kt, lambda t, plus c1. We know our initial velocity at time 0, 0, so c1 has to equal 0. So now we have our velocity formula is just some constant, which we don't know, times t. And in a question like this, it feels like we're not going to get anywhere because we're using something we don't know. But we could work from here and say, well, I know that at 20 seconds, I get to 100 kilometers per hour, which is 250 over 9. And I can use this and say, hey, I can actually find out what its lambda is. It's 25 over 18. In order for my velocity to be at 100 kilometers per hour at 20 seconds, I can solve for lambda. And now that you have that, well, we can integrate to find our displacement. Add 1 to the exponent and divide. Again, you know that your initial displacement is 0 when time is 0, so that means C2 is 0. Plug in 20 seconds. And if you accelerated at a constant rate from 0 to 100 kilometers and got to 100 kilometers in 20 seconds, which is not that fast. Maybe this is like designed to be the most fuel efficient. There's probably formulas out there that they can make the car the most fuel efficient possible. And you would have traveled 277.8 meters. 3 decimal places, I'm sure it was 277.7778 as a result. So again, it shows you, even though you don't know something initially, what we can do is we can just put things in two formulas, put things into our acceleration, velocity, and displacement, use our integration to work through that. And as in this case, we did have enough information to solve. Again, these questions, when I look at it initially, I would say, ooh, I don't know if I have enough to do this. And there's no direct way to do it. You have to go through the steps all the way through. Okay. Now we've used we've got a couple of new formulas for averages. We have old average formulas, and we found out that we can find the average of something also from the integral. So our average velocity, this is, if you can use the first formula, is what we've always done. How far did you go? How long did it take you? That's going to be your average velocity. That's a really easy way to do it. Okay? But we can also now take our velocity equation, do the definite integral from a to b, and divide by 1 minus 1 over b minus a, and get that as well. Okay? This part here, just to make the connection. How do we do a definite integral? Step 1 is we would find this integral. Would you agree that the integral of velocity is displacement? So you would get displacement and put it in square brackets and put a to b. And then you plug in b, subtract, plug in a. Can you see that that's exactly the same as the original formula we always use for average velocity? Okay? So use the original formula whenever you can, because I hope it makes sense to you. How far did I go? How long did it take me? That's going to be my average velocity. But you might get this disguised as a velocity graph where they don't give you enough information and you have to calculate the area underneath to get your displacement. So it's neat to see those connections. Average speed, right? Average velocity is displacement over time. Average speed is the distance you traveled over time. So then we have to have the absolute value in there. And average acceleration, of course, is how much did your velocity change over time? And that would be the same thing with the integral. So a particle moves along the x-axis so that its velocity at any time is given by v of t. In which direction, left or right, because it's moving along the x-axis, is the particle moving at t equals 5? Justify. Okay? So we can find v of 5 by plugging it into the formula. We get 6. Positive numbers will always be moving to the right. Negative numbers moving to the left. If we wanted to find the acceleration at t equals 5, we'd have to use our derivative, plug in 5, and okay. Question was bothering me because I had no units, but there are no units in this question. So given that x of t is the position of the particle at time t, and an initial condition at time 0 is 12, find x of 3. So x of t is your displacement, because it's moving along the x-axis, and they like to use this function. I find the function x of t very odd because you're almost always using x as the variable, and like f or g or h as functions. To use x as the function is a little bit awkward, but they use x of t to say it's moving along the x-axis. So here x is just a function notation. So here is a new idea. Okay, one thing we could do, right? One thing we could do is we could integrate and get back to the original equation, plug in 0 and 12 and find c, and then take that and plug in 3. That would probably be your gut reaction, how you would solve this question. Okay. But we're going to start using more and more accumulation of change. So if I do the integral from 0 to 3 of the velocity, that is describing how much the displacement has changed from 0 to 3. It's an accumulation of change. And if I do that, that'll be x of t from 3 to 0, which will be x of 3 minus x of 0. I could plug this into my calculator. These are often calculator questions with the equation that I had. And I could figure out that the accumulation of change is negative 16.5. I'm going to take out my calculator. Sorry, I'll get everything typed in here while you write this down. So in my graph, I typed in the velocity, and I can graph that. And on my graph, I can go second, calculate, and I can do number 7 from 0 to 3. And it shades it in there and shows me that I get negative 16.5. Okay? That means wherever you started from, 3 seconds later, your displacement will be negative 16.5 from where you started from. In this question, it tells us we started at 12. If you started at 12 and your displacement is negative 16.5 from there, does it make sense that at x of 3, you would be at negative 4.5? So often you will see, and I'll write it in here, often you will see on the exam, they will show something like this. X of 3, or you could show it like this. This is accumulation of change. If I want to know where I am at time equals 3, I could say, this is where I was at time 0, and I'm going to add my accumulation of change from 0 to 3. of my velocity. Earlier on, I was talking about an example of my weight as a 3-year-old changing to a 7-year-old or a 10-year-old. If you knew my weight as a 3-year-old, and it was like you gained 40 pounds from 3 to 7, well, you would know how much I weigh at 7. You would take what I initially weighed as a 3-year-old, took the change that took place and added it, and then could say, well, if you were 25 pounds as a 3-year-old, and you added 40 pounds, you would be 65 pounds as a 7. Oh, I have no idea where I would find it. But we probably all have data somewhere of how much we weighed when we were 3. We could figure this out. So I like this idea, okay, especially on a calculator. This is the other option for us. Well, here, no, this is showing getting the 16.5 by hand. The other option for us would be to integrate, which would give us t cubed over 3 minus 3t squared over 2 minus 4t plus c, and figure out that c is equal to 12, because we have an initial condition that when time is 0, it's 12. Then we would get t cubed over 3 minus 3t squared over 2 minus 4t plus 12, and you could plug in 3 and do all the math with plugging in 3. Of course, if you have a calculator, this is so much quicker and so much easier. Find the total distance traveled by the particle from time equals 0 to time equals 6. So if I just went to my calculator again, and I went from 0 to 6, part of that area, part of that displacement is negative, and part of that displacement is positive. But this question is asking for the total distance, not the displacement. If you have a calculator, the quickest way would be to put absolute values. Okay, I'm going to show you how to do that probably as quick as possible on your calculator. So if you had your calculator set up the way that I did, okay, yeah, what is this? This is just numbers? Oh yeah, okay. If you have your calculator set up the way that I did, and you already in y equals had your equation, under your math button, number 9 is the integral. We're going to want to find the integral from 0 to 6. And instead of rewriting my equation in here, I'm going to put my absolute value bars, which are a little bit hard to find on the calculator. You have to go to the math button and over to number. ABS is absolute value. I'm going to just check. Is it in any of the shortcut menus? Yes. Alpha F2 has the absolute value shortcut there as well. And then inside, I'm going to go alpha F4, and inside I'm going to put Y1. We're still, oops. And we're still doing the derivative with respect to x, because y1 was an equation with x. We push enter here. And we get 31.333 as our total distance. If you were doing this by hand, you would have to first find your x-intercept. Your x-intercepts are at -1 and 4. You could find those x-intercepts by setting t squared minus 3t minus 4 equal to 0. I'll do that right here. T squared minus 3t minus 4 equals 0. So you find your x-intercepts and say, oh, because between 0 and 6 I have the x-intercept of 4, I would have to find the area between 0 and 4, and then find the area between 4 to 6. And because the area between 0 and 4 is negative, I put a negative sign out in front to make it positive, because we're talking distance here. Distance has to take every negative displacement and make it positive. Can you see why they let you use a calculator for a question like this? Just the plugging in the numbers is really annoying. So probably the hardest thing in kinematics is just keeping track of what you're trying to find. Because speed and velocity are so close, distance and displacement are so close. Now we're trying to find an average speed. Average speed is distance traveled over time. Average velocity would be displacement over time. Do we know the distance? Yes, we figured that out to be 94/3. Do we have the time? It's 6. You don't need your fancy integral formula here because we already know the distance traveled. Time is really easy to figure out as well. For what values of t is the particle's instantaneous velocity the same as its average velocity between 0 and 6? We know that the average velocity, we can figure it out with the integral, or we could figure it out with displacement. This second, do we have a function for our, sorry. Change in displacement over change in time. But if we don't have those values, then we could use our average velocity formula this way. Because this integral from 0 to 6 of your velocity, this part right here will give you this part right there. And plugging in the numbers, you can do that with your calculator. You're going to get -1. So then when is it going to equal that -1? I have to use quadratic formula, of course. And in the quadratic formula, you'd have the plus or minus. But in the context of the question, time could only be positive. So you have to take that into consideration. Realize that 3 minus the square root of 21 over 2 is negative, and cancel it out. So I highlighted instantaneous velocity before. That's just your velocity formula. Your velocity formula tells you what the velocity is at that instant. We're making that equal to the average velocity, which is -1. All right, we'll do one more question today. Car is traveling on a straight road with a velocity of 80 feet per second at time equals 0. And the car's acceleration is given by this graph. So I took that graph, broke it up into triangles and rectangles, and you can add the areas in each of those sections. And a lot of what you're going to do on the exam is have graphs like this and interpret results. So acceleration at 15, well, acceleration at 15, you can just plug in and get -20, because this is our acceleration graph. So as you do your take-home quizzes, you're going to find that really what you're going to be training your brain to do is understanding what does my graph represent? What does it tell me? What does the area under that graph tell me? Okay. Now to find the velocity at 15, this is very typical of these questions. The main understanding that we have is that if you have the acceleration, the area under the curve is an accumulation of change of that. So what does it mean? In the first 10 seconds, your acceleration increases by 150. So you're going to be going 230 feet per second. It's just a little bit faster than I can run. Okay. Then between 10 and 30, you've got negative numbers here. So that accumulation of change means our velocity is going to be going down. If we want to figure out the velocity at 15, we can say our velocity at 15 will be where our velocity started with plus accumulation of change. And so we have our starting point, and our integral is that accumulation of change. Having that as an idea makes this question really easy. We know we started with 80. We could add our 150, and then from 10 to 15, we'd have to subtract 50. And we would be at 180 feet per second. Just looking at the graph, see if you can solve part B before we write any math down. At what time other than 0 is the velocity back to 80 feet per second? Okay. Again, think of, you have a starting point. We started at 80. And the area under that curve is your accumulation of change. From 0 to 10, you've went up to 230. You need to get it back down to 80 again. Can you see at 20 that the positive that was added would get subtracted again? You'd be back to where you started from. So I can see directly from my graph that the answer to this is going to be 20. Because that area above the x-axis from 0 to 10 gets canceled out with the area below the x-axis from 10 to 20. Part C, on the time interval from 0 to 35. What is the car's absolute maximum velocity and absolute minimum velocity? Sounds like an extreme value theorem question. What do we need for an extreme value theorem? We would need continuous. Okay? Since we have the derivative, remember that having the derivative implies continuous, so we could use the extreme value theorem. What do we check for critical points? We would check every place where the derivative was 0, which is 10 and 30, and you would check your endpoints. So our initial was 80. V of 10 would be 80 plus the change of 150, which is 230. That is, once we find all of them, you would say, I know that that's the absolute max because it's the biggest. We'd check V of 30 minus 20. We would check V of 35, the other endpoint, and get 5. And from this, we could see our absolute maximum and absolute minimum. This is using the extreme value theorem. Okay, and if they asked you to justify it, you would have to notice that since the acceleration exists, and acceleration is the derivative of velocity, velocity is continuous. If you're using the extreme value theorem, intermediate value theorem, and mean value theorem, and don't quite know how to say it, just say it anyways, that we know the function is continuous. And maybe if you don't give a reason, you will still, in that 1 mark, probably get half out of 1. Whereas if you don't say anything about continuity, they'll give you 0 out of 1. All right, that's where we'll end for today.